Hello everyone. So today we're gonna talk about the atomic structure. Atomic structure, as you know, is a very huge topic, so we will be dividing it into many parts. So I think that you might be aware of some basic concept of atomic structure. Okay, the Rutherford experiment and many more things like J.J. Thomson experiment or the discovery of electrons, neutrons, the R. Millikan's experiment. So I think that you might be aware of all these. So we'll start with a new concept today, and that is wave nature and blackbody radiation. Here it is. So wave nature, we're gonna talk about wave natures today. So what exactly can be wave? A wave can be a disturbance that travels through a medium, and that's the definition of a wave. It's a disturbance that travels through a medium. So for instance, you can imagine this like this. So you have a rope here, okay? You have a rope tied to a rigid support, and then you give a push or pull upside down forces on this rope. So what will happen then? The rope will get some disturbances, some disturbing forces, okay, and it will turn something like this, okay? It will look something like this, and what we see here is all these curvy things is all the disturbances, okay? These all are the disturbances. So how we made these disturbances? We gave it some force. So in atomic structure also, when we talk about wave, so there is some force that give us wave, and we will talk about it in the later concepts. Right now we will be focusing on what is a wave. Okay, so you know now what is a wave. So let's go to some parts of wave. So as you know, so as you can see here, this is a wave. The wave looks something like this, and now let's look at the structures, like what can we see in this diagram. So the first thing that we have is we have a distance between two waves, okay? Like this is an upper mountain, like this is a upper mountain and this is a valley. So these mountains and valley have a name, okay? These mountains are known as crest, and these valleys are known as floor. Okay, so crest and draw. Now the distance between crest and draw, we get it as wavelength, okay? The distance between any two consecutive similar points, okay, they will be similar, like this and this, or this and okay, I don't have that, okay, this and this, or this and this. So any two similar points, the distance between them is what we call that wavelength. So we denote wavelength by Greek symbol lambda, okay, and this is called the wavelength, okay. The next thing is the height of valleys and mountains, okay, the height of crests and trough, okay. So this is what we call amplitude. Amplitude is we denote it by A and measure it in meters. Wavelength also we measure it in meters, okay. So now let's talk about some other concepts of waves, okay, some other things that wave has, the properties of waves, okay. First thing is the frequency. So frequency is nothing but number of waves that is passing through some time, okay, and it can be also be like after solving this equation, actually in many examples or experiments, after solving this equation, we get it as 1 upon t frequency. We get it as 1 upon time. Okay, so this is easy. Yeah. Okay, so now to make the concepts a bit more clear, we have some example. Okay, so this is an example. So what you have to do, you have to imagine a railway track and a pole which is near to the rail track, just beside it. Okay, and a train passes through it. Now train has some carriages. Okay, so what we have frequency is what the question what I can ask is, what is the frequency of carriages? Okay, what is the frequency of carriages? So frequency of carriages would be number of carriages that are passing through unit time. Okay, in unit time, that let's say there are 15 carriages that pass through the pole in 5 seconds. So what will be the frequency? 3, right? So we have to do it like that. Okay, so now this is the pole. Okay, and the train is passing. So similar to the train, we have wave. Okay, and what are the carriages here? These are the crests and troughs. So we can say the number of crests and troughs in a wave that pass through some time. Okay, we also denote it as 1 upon t. Okay, it passes through 1 second. Actually, the number of carriages, the number of crests and troughs that passes through 1 second, passes through something like what we can refer to anything. In this case, this is the pole. So that passes through a pole in 1 second, or 1 upon time. Okay, so the next thing that we are going to talk about is the speed of a wave. So if a wave is moving, it will have some velocity or it cannot move in. Yeah. So the speed of wave is mu times lambda. Mu is nothing but frequency. Okay, this can be written as like, this is v only, just this one is straight and other one is curved. Okay, so this forms your mu. So mu times with lambda. So frequency times time. Then just write it like that. Well, that's not correct actually. Okay, so mu times lambda is your speed of wave. Okay, so now this is the derivation. First thing you should ask about any derivation is how. So you should look into the formulas and ask how this is derived. Okay, so how we derive this formula? We derive this by nothing but the frequency and lambda itself. Okay, so we have frequency, that is 1 upon t here, and we have lambda. Okay, so lambda is measured in is length. Okay, the dimension you can write it as length, and the dimension of frequency is t raised to minus 1, t minus 1 actually. T minus 1 is the dimension of frequency. So now we want to relate time and length. Okay, so when we relate time and length in this format, velocity is Lt minus 1. Dimension formula for velocity is Lt minus 1. So when we arrange them in this way, length we get it as lambda, and time for mu, okay, T minus 1 for mu. So when we arrange them in this manner, we get mu lambda, and this is what we call it, the speed of wave. So far what we have learned is all that you might have learned in your lower standard. Okay, like frequency, amplitude, and lambda and wavelength. So you might have learned them, but now we are going to talk about something serious. Okay, so what it is, it's constructive interference. So what this is, okay, so it's nothing but when two waves interact, they form a third wave. Okay, when two waves interact, they form third wave, and this is what we mean by interference. And what is constructive doing here? Constructing means that it is adding. Okay, this is the waves are adding up. Okay, so consider these waves. Okay, so they both have same lambda. Okay, lambda is same in both the cases, and the amplitude is also same. Okay, so when you add them, when you add these waves, okay, amplitude is same in the direction. Okay, when this is upwards, this is upwards, it's down and down. Okay, it's like that. So amplitude and lambda both the same. Okay, amplitude might not be same, but then we actually take it as same, because in constructive interference we just talk about that only. Okay, constructive means you double the thing. Okay, in this case constructive means you double the things. Okay, so it will form something like this. Okay, when you add these waves, um, when you add these waves, okay, there's a add sign here. Okay, so when you add these waves you get a third wave, and what will be the characteristics of this wave? The lambda will be same. Okay, but amplitude will be doubled. Okay, amplitude will be doubled. Why? Like this can be just observed by you in a normal day-to-day life examples also, like you when you right, so you can imagine this also, where like someone is shouting in your class, and the another person also get excited away. I will also laugh, and he also start laughing. Okay, so when both of them laugh, the loudness is greater. When we actually combine the wave, the amplitude is greater in the wave. Okay, so this might help. Okay, took it from Google actually. So so the lambda is same, the wavelength is same, the amplitude is also same, and when these two adds up, the lambda, let's see this line, so the lambda is again the same. Okay, lambda is same, but amplitude changes. Okay, see the amplitude, it changes. Okay, here is smaller and here it is larger, so amplitude changes but wavelength is the same. Okay, so now let's talk about the opposite of this thing. Okay, the opposite of this would be the opposite of constructive, destructive interference, right? So what will happen when you interfere two waves, and here what we call as destructive interference. So it actually does not mean we are subtracting the waves, we are adding the waves only, but now the characteristics of the waves will change. Okay, how it will change? See, for here the crest is like this, and here the throw, the crest is replaced by a throw. Okay, so when these two adds up, this will subtract. Okay, in this case also lambda would be same. Okay, lambda does not change. Also your amplitude does not change. Okay, wavelength and amplitude are same. Okay, and what will happen if I add these two waves? What I'll get is nothing. Okay, when I add these two waves, okay, these two will cancel each other. This two will cancel each. Okay, so these two will cancel each other. This and this will cancel each other. This and this will cancel each other. This and this will cancel each other. So you will not get anything. Okay, you will get a null wave. Okay, there is nothing here. Okay. Everything is destructive. Okay, everything is destructive, and you don't get anything there. Yeah, this might help. Okay. See, the amplitude should be same also. Okay, amplitude should be same when we talk about this thing. Okay, and lambda obviously should be or wavelength obviously should be same. Okay, so when you have a destructive interference between these two waves, what you get is nothing. Okay, so these and these are cancel each other, the waves cancel each other. So now let's go to the other concept of atomic structure. Okay, now this is a very fascinating, bit challenging concept. Let's see what it is. Yeah, the electromagnetic radiation. Okay, what is electromagnetic radiation? So radiation that consists both of electricity and magnetism can be talked about as electromagnetic radiation. Okay, we can say it as electromagnetic radiation, and this is a very important topic. Was first explained by James Clerk Maxwell. You should remember his name. He is a very great scientist. For more information, if you want to know more about the electromagnetic radiation, you can study his work. He has his book. He has written a book. You can study that, and you can learn more about electromagnetic radiation. Okay, so now, what would be the basis of his theory? What would be the basis of James Clerk Maxwell's electromagnetic theory? So what he experimented, and he concluded that when a charged particle accelerates, alternating electric and magnetic fields were produced. Okay, electric field and magnetic field are produced when he did experiments. Okay, and transmitted in form of waves. So these electromagnetic these electromagnetic radiations were transmitted in form of waves. Okay, so he named his theory as electromagnetic wave theory. Okay, you can study more about that on internet. Okay, so now this is interesting. Okay, this is graph of electromagnetic wave. This is how an electromagnetic wave looks like. Okay, so here you can see this. These are crests. Okay, these are troughs, and now there's something strange. Okay, this is going like this. Okay, but this is going perpendicular to this. Now this is a property. Okay, the property of electromagnetic waves, that when you represent them as graphs, they are perpendicular to each other. Electromagnetic waves travel always in perpendicular direction. They both are perpendicular to each other. So you can see from the diagram, it's a bit confusing, but you have to go with it. Okay, so look at it. Okay. This is electromagnetic radiations. Okay, these are the radio waves. These are infrared. Then here we have the visible range. You can see the colors. This is the ultraviolet, and X-rays here are here, and gamma rays. Okay, so we have all these waves. So you can note out the wavelengths. So these are a meter from 10 raised to minus 16 to 10 raised to 8 meters. Okay, the radio wave, the wavelength is greater than actually a kilometer, right? Greater than 10, or actually 5 kilometers. Greater than 5 kilometers, the wavelength is so large. Now when you look at this thing, okay, visible light range. Okay, so here from 400 in nanometers. Okay, 400 nanometers to 700 nanometers. This is what we call visible light. Okay, and one point you have to note, that light is an electromagnetic wave. Okay, light is an electromagnetic wave, and this was proved till that time. Okay, till the time when these electromagnetic radiations were there, light was proved a wave. Why, we will see later on in this video. Okay, why light was considered as an electromagnetic wave and not as a particle. But then Einstein suggested that light behaves as a particle also. Okay, we'll talk about it in the photoelectric effect. We'll talk about that light can be imagined as a particulate, as in a particulate nature. Okay, and one particle of light is called as photon. Okay, so let's not jump into that and look at it. Okay, so this is a visible light. So what you see here is the spectrum. Okay, the rainbow like thing here, and this so like everything you see here. Okay, when you see a red object, when you see a yellow object, when you see a green object, you should remember that it's not the color of them, but the light, what they reflect, varies. Okay, so now if I make a device, okay, if I have a device that can change the wavelength of any object, like if I have a ball here. Okay, if I have a ball, and this reflects light of 700 nanometer. Okay, so what I will say, this ball is red. Okay, this ball is red because in 700 this is showing us red. Okay, for 700 nanometers wavelength, the color of the light, color of the electromagnetic wave would be red. Okay, but now if I have a device that can just make this ball change its reflecting wavelength to, let's say, 500 nanometers. So now what will happen is this red ball will change to green. Okay, so this would be magic. Okay, this all fiction till date, but I believe that this is going to happen someday in future. Okay, this will happen someday in future because we are going advanced in technology. We are so advanced today, and we will be more advanced in coming days, in coming years. We will be more advanced than this. Okay, so this is a very good topic, diffraction. Okay, so you might have read about properties of light. Okay, it reflects. Okay, it reflects or it bends. Okay, not taking the surface. Just a minute. Okay, if I have a surface here, so light comes and goes like this. Okay, this is reflection, and if this is some other medium, so light actually bends. Okay, light bends. So this is reflection and this is refraction. But now what we are going to study is about diffraction, and this is also a property of light. So what is diffraction actually? So it's some like if I have a wall, or a very thin wall. Okay, and what I do is I make a hole. Okay, in between this I make a very small hole, and now what I do is I make some light waves to pass through this. So there will be some waves that come like this. Okay, waves are coming like this. These are all transverse waves. So when these waves will come, if they are moving in this direction, when they actually get a direct contact with this hole, very small hole. Now this hole should be actually comparable to the wavelength of the wave. Okay, so this should be very small hole. What will happen when the light wave approaches this hole? What happens is it bends like this. Okay, it bends and it forms something like this, your Wi-Fi symbol. Okay, so this property of light, when it get a contact with the very small hole on a very small, very thin wall, it bends. This property is called as diffraction. Okay, and also you have to note something like this hole. If what we call this hole, we call this hole as slit. Okay, slit. Call this hole as slit. So this is the slit experiment, or can say it is like diffraction only. So on the basis of this diffraction property, many scientists conducted many experiments. Okay, and we will learn about them later. Okay, so this is one of them, Young's double slit experiment. So Young was a scientist who performed this experiment, the double slit experiment, and we will find out what he did with this double slit. Okay, let's see. Okay, so check this out. This is Young's double slit experiment. This is what it looks like. So here we have some waves. Okay, here are some waves. Now these diffracts into these circular waves, and now these circular waves again diffract to form this kind of structure. Okay, now what significance does it have? What will happen here is we will use the concept of our destructive and constructive interferences. Okay, so what will happen when these two waves, see, when from this slit one wave is diffracting like this, okay, one wave is diffracting like this, and from the other one is diffracting like this. So they are both interfering, okay. Can just see like this, okay. So now when they meet these points, okay, when they meet these points, this line, okay, this line has the destructive interferences, and the time when they meet at a very less angle, like when they meet like this will form constructive interference. Or when they don't meet, actually where they don't meet, it form as constructive interferences. And where they meet and they destroy each other, because these are both opposite, one is going like this and one is going like this. So when they both meet, actually they destroy each other, they form a destructive interference. And when we look at here, this is screen, okay. So when you look at these points, okay, we see something like this, okay. Now where this is black, okay, this is the destructive interference, and where this is a bit whitish or grayish, this is the constructive interference, okay. So now when this experiment was conducted with light, when we took a light here and we made some, like, when this happened, okay, so when light was passed through these slits, when light was passed, it showed the property of diffraction, okay. So when light showed the property of diffraction, and diffraction property was mainly actually observed when we took waves, okay. So light was then proved to be a wave, okay. Light was proved to be a wave because light can construct or destruct the other light wave, okay. So this experiment holds correct when light is taken as the reference point, or when light is used in place of wave. So when this happened, they saw that the experiment is correct then too, okay. So then they proved light, or they considered light to be constructive, or they proved light to be a wave, okay. So light was then proved to be a wave. Okay, so blackbody radiation. Blackbody radiation, a very simple concept. People don't actually study this concept because it sounds weird, actually. Yeah, I know this sounds weird and it's a very scary name, blackbody radiation, but actually this is a very simple topic, and I can actually finish this in only one slide, okay, half slide actually. This is a very easy topic. So this is what we mean by blackbody radiation, okay. Every object will radiate energy in the form of electromagnetic radiation purely as a consequence of its temperature. This is a law, okay. This is a theory or a statement given by a scientist on basis of some experiments, okay. And this is blackbody, okay. What is a blackbody? It is an idealized opaque object which absorbs all incident electromagnetic radiation, okay. So if I have a ball here, okay, so example so it absorbs all incident electromagnetic radiation, okay. So if I have something, let's say I have a pot here, okay. Pot looks something like this, and I have a cube here, okay. Simple. I have a cube. I can actually construct a cube, huh? I can just construct a cube. Shit, man. Okay, so look at this is a cuboid, okay. So if I think it is an idealized opaque object, it cannot exist, actually. It does not have the potential to exist on Earth. Okay, so this is gonna be black in color, everything. Why? Because it absorbs everything, okay. We actually cannot see this object, and if it exists also somewhere on Earth, we cannot see it, so we can't utilize this object. We don't know whether it exists or not. That's why it is written as idealized opaque object. Okay, this absorbs every incident electromagnetic radiation, so there's no reflection only. Yeah. When you look at something black in color now, it is reflecting nothing, okay, but it is absorbing everything. Now this is something like it will absorb everything and reflect nothing, so this is actually black in color only. And yeah, this is like that. So now we have some graphs, okay. We have some intensity versus wavelength graph. Now what this is, watch. Okay, so intensity is nothing but the, like, how much do you heat the object. Yeah, like if I heat some object at 400 K and I heat another one at 4 4000 K, so these both will radiate some other amount of energy, because we read earlier that the form of electromagnetic radiation purely as a consequence of its temperature. So as you increase the temperature, the electromagnetic waves are going to increase. Okay, so what are these graphs? Let's see. Okay, so the graph looks like this. This is the intensity here. Here we have the intensity, and here we have the wavelength. So this graph goes like this, but it never meets the x-axis. It is shown like this, all collides somewhere, and it goes like that, but it never meets. Okay, this can go till infinite. It only shows that when you increase the wavelength. Okay, when you sorry, when you decrease, when you increase the time, okay, the time also matters here. Okay, so then the wavelengths will actually vary. Like you can see here, it first goes up and comes down. So this are the wavelengths vary for time. Okay, so we can have a relation between intensity, wavelength and time. Okay, this graph. Okay, so it's all about the waves nature and like a blackbody radiation. Okay, it's all over today. It's all for today, and we will be uploading many videos for for others topic for atomic structure also. Okay, so there are many videos and you can watch every single of them. Thank you.